Welcome to this short lecture on the economic consequences of automation and AI. What I will do here is first to present some of the stylized facts of automation and artificial intelligence, and then move on to a simple economic framework that extends well-known models such that the extended framework can capture automation and artificial intelligence. The framework is deliberately kept simple such that a course like this can be taught at the bachelor's level and at the master's level, and nevertheless it conveys the message of how automation, for example by industrial robots or by artificial intelligence, impacts on the economy. What I will do is to basically extend the solo type of growth model that is well known to capture these new technologies. In the first part of the course, however, I will briefly talk about the stylized facts, and I usually like to motivate these presentations on automation by two different pictures. The first one is from a car factory of about 100 years ago, where we see that production is very labor intensive. We have this production hall here, and we have the two types of production factors, human workers and physical capital in the form of this simple assembly line, and they together produce output. And that's basically capturing in a picture what we economists do with the Cobb-Douglas production function, where we assume that workers and capital combine to produce output, and both of them are necessary inputs. So without humans, you could not produce any output here. Now we fast forward 100 years and Google modern car factory, and the picture that we get typically looks like this one here. We don't see any workers anymore. Instead, we see two different types of physical capital. We still see this assembly line, but now in a much more modern form, of course. And we see that workers have been substituted away by another type of capital, by the industrial robots. Of course, this does not hold true for all tasks, but it's kind of illustrating quite well what is happening in the economy. That production process is changed in a fundamental way, but we have the possibility now, for the first time in history, to perfectly substitute away human workers by another different type of physical capital. And we see here already that this changes the production process in a way that it also changes the implications of economic growth models fundamentally. Because suddenly what we can do here is we can produce output without any human labor input, and we do not have a Cobb-Douglas type of production function anymore as we had it here, but more an AK type of production function, where there are no diminishing returns with respect to the production factor physical capital. So in such a setting, if you put this into a solo type of growth model, what you would get is all kinds of interesting effects. Perpetual economic growth becomes possible in such a setting just by the accumulation of physical capital. So you have accumulation of assembly lines, and you stuff these assembly lines with the industrial robots, and then you can produce more output, and per capita GDP increases. That's one implication. Another implication is that the labor share decreases, which is exactly what we see in the data, and you can even get more out of such a model, and we will come to this in the second part of the course. But before going there, let me just talk a little bit about the technologies that are used to automate labor and how they developed in the last couple of years or decades. The first one we've already seen, that's the industrial robots that we've seen in the picture before. And they are well suited to automate mass production. So you have certain routine tasks that have to be performed on an assembly line, and you can very easily substitute the human workers doing these repetitive tasks by industrial robots. That's already done on quite a large scale in many factories, particularly in the automotive industry, but also in many others. And that's kind of the automation of mass production. However, it's also possible to automate customized production. The technology that made a lot of progress in this area are 3D printers. So 3D printers are, for example, used to produce hearing aids, where each single one of them has to fit the ear of the customer or the patient. It can be used to produce implants. It can be used to produce spare parts that are only needed very infrequently, and so on and so forth. So a very customized type of production, which would have been very labor intensive in the past to fit each of these single products to the particular customer. But nowadays that's automatable through 3D printers. The next item on the list is autonomous driving. And that's particularly important because it affects such a large group of workers. Taxi drivers and truck drivers are in many countries one of the largest occupations where the most people work. And if that can be fully automated, that would make a quite large impact on the economies under consideration. We see autonomous driving now making quite a lot of progress in the US and in China. Europe still lags behind in this area. And finally, we have machine learning and artificial intelligence, which can automate cognitive tasks. And that's quite interesting because just a few years ago, people would have said, well, you have to educate yourselves better, you have to get high skilled, you have to move into cognitive tasks because that's something that cannot be automated. And in the last couple of years, we've seen such huge progress in automating cognitive tasks that it is really breathtaking. So we are now able to automate writing, translating, idea generation, coding, so programming skills are not that important anymore. Big data analysis, of course, can be done best with these types of machine learning and AI algorithms. Reasoning models that even show how they think, quote unquote, and they can come up with quite sophisticated chains of thought in this case to get to a certain result. Diagnosing diseases, for example, that's a pattern recognition exercise basically, so that's no surprise that algorithms are very good at doing that and that they surpass human doctors in diagnosing diseases. Even doing science in material science or in drug development, where it's often necessary to simulate the outcome of different combinations of inputs, it's almost impossible anymore to do this without machine learning and artificial intelligence. So the bottom line here is cognitive tasks are also automated on a large scale, and that's what everybody knows at least since the introduction of ChatGPT in the year 2022. And as I said before, the purpose of this presentation, and particularly the second part of the lecture, is to design very simple economic models that can make sense of the impact of these new technologies on economic outcomes, where the distinctive feature of these technologies is that they are not anymore as complementary to human workers as in a Douglas production function, as an assembly line, for example, that has to be operated by humans, but that these technologies can perform the tasks autonomously without any human supervision or input, and thereby act more and more as a perfect substitute for labor. And that's a very different mathematical property that the production function then has, and we will later see how this could affect economic outcomes. Before we go in this direction, I'd like to say a few words on the development of the different technologies that we've seen before, or at least some of them. And here we see the number of industrial robots worldwide that are in operation in different firms. The data of that is being kept track of by the International Federation of Robotics. That's an association to which the member firms that produce the robots report where they exported the robots to, and then you can construct out of this, with an assumption on the depreciation rate, the stock of robots that has to be currently in operation in the different countries. What we observe here is that throughout the 1970s and 1980s, the stock of industrial robots was actually almost negligible and close to zero. The first industrial robot was introduced in the 1960s, and then, say, until the mid-1980s, the stock of robots was almost zero. Then growth in the stock of robots set in, but it was still rather sluggish until the global economic and financial crisis lasting from 2007 to 2009. Afterwards, the stock of robots, industrial robots in production, really took off. Since 2010, we've observed growth rates at the order of 10 to 15% per year, and that's much faster than growth in the workforce of any country or per capita GDP growth in any country. So we really see an intensification of automation in terms of industrial robots since then. What we also observe is that the stock of robots more than quadrupled since 2010, so over the past 15 years, from 1 million operative robots to more than 4 million operative robots in the year 2023. So we've seen that the stock of robots has increased worldwide, but another question is where these robots are used. Here we see a world map where the robot density, that's the number of industrial robots per 10,000 manufacturing workers, is highest and where it is lowest. It's higher in countries with a dark color and lower in countries with a light color, where there are many countries with no data, so the white countries here, but that's synonymously almost with having no robots or a very low number of robots. What we observe here is the first thing is perhaps not so surprising. The countries that are at the technological frontier use robots more intensively. US, Western European countries, Northern European countries, Japan and South Korea. But another aspect is quite interesting, and that is that there is a lot of variation among these countries. So some countries use robots much more intensively, such as South Korea, Japan, Germany, and Italy, than, say, France, the UK, or the United States. And one of the reasons could be or has been identified in the literature is population aging. So these are the countries with the lowest fertility rates worldwide that use robots most intensively, South Korea being a forerunner, Japan, Germany, and Italy, and countries with higher fertility rates or lots of immigration in the past use robots less intensively. Particularly interesting that's for the UK, which had seen quite a lot of foreign immigration after the enlargement of the European Union from Eastern European countries. So automation was not that much necessary, right? So if you have lots of workers, you have less pressure to automate. So countries that are susceptible to demographic changes more, they are also the ones that invest more in automation technologies to cope perhaps with labor shortages and with high wages in this case. Now, what about artificial intelligence? That is definitely a topic that we all are very interested in at the moment, that we've seen since 2022, since the introduction of ChatGPT, that things have increased quite strongly, and also progress has been quite fast in what these algorithms, these models can do already. What we see here in this first picture is the cumulative number of large-scale artificial intelligence models by domain since 2017, and we see that until 2020 there was almost nothing going on. Then large language models increased a little bit, but only in 2022 there was really this takeoff, and we see that nowadays we have much more than 200 large-scale AI models in the domain of large language models, but we also have many we have made a lot of progress in other areas such as vision, image generation, video generation, audio generation, speech recognition, and so on and so forth. So there is really a lot going on in terms of the number of large-scale models available. While the number does not tell us much about the performance of these frameworks, I find the next picture, both are taken from our World in Data database, more illuminating even, and that is the performance of AI models relative to human performance. Human performance is normalized to 0 here, and at the introduction of AI in a certain domain, its performance relative to humans is normalized to -100. And what we observe here is that in all of these domains, artificial intelligence models were completely outperformed by humans just 1 to 2 decades ago, right? And then within a few years, artificial intelligence has made a lot of progress, such that in all of these domains, machine learning algorithms, AI models, are more capable than humans already at this point. So, and in some cases, we were overtaken quite fast, like here in reading comprehension, that happened within 2 years, basically. Also, language understanding, that was only 1 year in this case. So the performance increase in these artificial intelligence models has been hugely impressive, and there you can see why there is a lot of talk in the media about humans being outcompeted by artificial intelligence. So now the crucial effects and key questions based on these stylized facts that we've seen now are: what are the economic effects of automation on the productivity in an economy, income growth and welfare? So that's kind of how do these new technologies affect us on average. But there are also concerns with respect to the distribution of income between labor and capital, but also between different types of labor. So income inequality, the third item here. You could very well imagine that if you are able to automate routine tasks, that some workers will see their wages decrease, perhaps their employment prospects fall, while other workers may benefit. Those who supervise production, those who maintain the robots, and so on and so forth. And both of these effects we will also analyze. And of course, also the implications for employment as such, which seems to be one of the greatest concerns in the public debate on automation and artificial intelligence.